All right, guys, congratulations. We are on the last topic for the quarter, and this is on redox reactions. You learned from general chemistry, probably the oil ring mnemonic, which is oxidation is loss of electrons and reduction is gain of electrons. Or some people learn Leo the lion says grr. That's another one. Gen Chem throwback, iron then, iron metal going into iron 3 plus ion, so ferric ions. Is that oxidation or reduction? So if we look at the charge here, this is 0, oxidation state, going to +3. Then iron's thought of as losing 3 electrons. So that's a loss of electrons, which means it's oxidation. Now don't freak out, we're actually not doing much of this. We're going to simplify it into things that organic chemists find useful, which is thinking about carbon, oxygen, and hydrogen. So in a very simple sense, think of oxidation as an increase of oxygen, and specifically the number of CO bonds. Then you can think of reduction as the loss of CO bonds, so a decrease in the number of CO bonds. Another useful definition is that reduction is the gain of hydrogen, meaning the increase of CH bonds. And so the reverse of that would be oxidation, the decreasing of number of CH bonds. So using these definitions here, let's look at these examples and see if we can identify oxidation or reduction, or maybe it's neither. So there's at least one neither in this set. First, let me give you an example. Right here, I have carbon bonds only, and here I have a carbon-oxygen double bond. So clearly we've added oxygen and we've added the number of CO bonds. So this is going to be oxidation. All right, now go ahead on your own. See if you can spot the neither, or see if you can tell oxidation versus reduction. All right, we're back and we're looking at a CO bond here, which is no longer there. So this is a decrease of CO bonds. So this is an example of reduction. This is a carboxylic acid going to an aldehyde. That's reduction. Let's look at this alcohol going to a ketone. We now have an extra CO bond. So this is oxidation. So in general, this is a very good series to learn. Alcohol to ketone, or alcohol to aldehyde is also oxidation, and aldehyde to carboxylic acid is oxidation, and going the other way is reduction. Here we have a hydrogen over here, and here we've added 2 hydrogens that we didn't have before. So here's the one I had before, and then here are some new ones. So I added hydrogen to get an alkene. So this is a reduction. In this example, I've got hydrogens here and here and here. Now let's see what happens. We added a CO bond, so that looks like oxidation. But then I also added a CH bond right here. So just sort of highlighting my new bonds. So I actually have an oxidation and a reduction. So in an addition reaction, which are all the reactions we've been learning so far, reactions to a pi bond, turns out that you're adding groups that cancel each other out. So this is going to be neither. And then finally at the end here, let's see what happens. I have hydrogens here, and now they're carbons with methyl groups only, no hydrogens. So this is the reverse of this top one. So this is an oxidation. And that's because we're losing CH bonds, so we're decreasing that is oxidation. So first we're going to learn about reductions, and then we're going to learn about the oxidations. For reductions, take a look at the functional groups and what's changing about them. We're going from an alkene to a CC bond. This is an alkane. So the pi bond is adding hydrogens, and let's draw the hydrogens that were there before, and let's draw the H2, the new hydrogens would be here in order to make the alkane. So we're adding hydrogen. Now this requires a catalyst of either palladium metal or platinum metal. And the way that I envision this reaction is I have a surface, it's a catalytic surface of palladium or platinum. And you may think, wow, platinum, that's expensive. And it is, but that's a metal that's commonly used in things like catalytic converters. So these are metals that help to reduce the nitrogen oxides that get formed when your car undergoes, when the gasoline undergoes combustion, so in the combustion engine. So we have hydrogen molecules on the platinum or palladium surface, and then you have your alkene come in from the top. And as your alkene comes in, you could have cis or trans alkene, doesn't matter. Your hydrogens are going to add on to the same side. Because you're making an alkane and you have bond rotation here, you do not have a preserved stereochemistry. But later you'll see that with triple bonds that you can. But in any case, this is considered a syn addition because the hydrogens are adding on to the alkene from the same side. And you'll be able to see that if you had a cyclic structure here. And so we'll see that on the next page. We also have a triple bond. So instead of an alkene, we can have an alkyne, and that reacts in the same way, but the difference is you have to add more hydrogens here. So we didn't have any hydrogens here, and now all of a sudden you have 4 hydrogens. They came from 2 hydrogen molecules. So we usually say 2 molar equivalents, meaning 2 H2s have to be used, or more commonly, we just say an excess of hydrogen. And sometimes that's specified and sometimes not, but pretty much if you have alkyne and it makes alkene, that alkene is just as reactive and it's going to go to the alkane. So as I was saying, we have a cyclic alkene. So in this example, we're doing the hydrogenation or addition of H2. Now see how in a ring you can preserve the stereochemistry. So you see syn addition here. I want to point you to a common example, which is sometimes deuterium used instead of hydrogen. When deuterium is used, and remember that's a hydrogen 2 isotope, so it's a heavier isotope of hydrogen 1. That means that you still have the same reaction, but instead of hydrogen 1, you have hydrogen 2. So we just show that with capital D. So you'll often see that on exam questions, MCAT, PCAT, DAT, all those exams. All right, now these next 2 reactions, you don't have to memorize right now, but you will use them to solve problems. So I will provide them only because we're technically covering them next quarter, okay? But it's basically the same reaction. We have an alkyne here. And notice that we're stopping it at the alkene. Now remember before I said an alkyne making an alkene, and the alkene is just as reactive and you'll get alkane. However, we're adding a reagent called Lindlar's catalyst in this case. So even though we're doing hydrogen on platinum or palladium, Lindlar's catalyst helps to slow that down so that you can stop it at the alkene. So the way I picture this reaction is I've got my palladium or platinum surface, and then I've got a layer of lead or barium sulfate or something, quinoline, that usually reduces the reactivity of that metal. So that means that it's not able to go all the way down. It will stop it at the alkene. And now notice the stereochemistry. This is syn addition as well, because it's basically the same reaction as the one before. This alkyne comes down and then you have the hydrogens adding on the same side. So those hydrogens adding on the same side are right here. So here's one hydrogen and here's the other. And when they're the same side, then the R groups are the same side. So this is a cis alkene that forms. For the next example, we have an alkyne again, but this time we want to be able to make the trans alkene. So how do we do that? This one is with sodium or sometimes with lithium metal. So it's got its valence electron. It's in group 1. And usually how that reacts is through what's called a free radical or unpaired electron mechanism. Now that's going to be taught next quarter with alkyne reactions, so don't worry about it now, but just know that there are 2 separate methods for making alkenes from alkynes, and one will make one cis and the other will make it trans. So hydrogenation in general is the addition of H2. And whenever we use H2 as a reagent, we get syn addition. Now we can get hydrogenation using sodium or lithium metal in liquid ammonia, but that's going to give us anti-addition. And the source of hydrogen in reaction C, we have 2 hydrogens getting added on, but they're opposite side to each other. And that must come from the ammonia. So it's sort of weird to think of ammonia as a kind of acid, but that's what's going on here. And this is liquid ammonia, so this is done at negative 35 degrees Celsius. So before we move on to oxidations, let's review all the reduction reactions that we've learned so far. So the first reaction is with an alkene, and I made it cyclic so you can see the stereochemistry. You can add H2 or D2, which is an isotope of that, and you have platinum or palladium metal as a catalyst. So in that case, you get syn addition of hydrogen or deuterium, whichever one you use. And of course, you can have the enantiomer of that, but this is achiral, so there is no enantiomer. In Chem 262, you'll learn that alkynes can give you alkanes, alkenes that are cis, or trans. And so here are the three different reagents we just covered. Go ahead and take a minute and just write that down because it helps to have it all in one place.